Okay, just as in the case of deadlock detection, for avoidance also we're going to look at two algorithms. The first one is going to be based on the graph. The second one is going to be a more formal algorithmic version. So this first one, resource allocation graph based algorithm, it works again if you have a system with only one instance of each resource type. This is something we have discussed multiple times now. You're very familiar with. So this becomes a sort of special case where you have only one instance of each resource type. Then the resource allocation graph itself helps you to detect a deadlock, avoid a deadlock, do a lot of stuff. Otherwise, in the general case where you have multiple instances, you need a more formal algorithm, which we'll be looking at in the subsequent segment. So right now, we'll keep life simple. We assume there's only one instance of each resource type. The RAG is given to us. How do we avoid a deadlock? Right, so if you remember about the resource allocation graph, it has something called the request edge and something called the assignment edge. So a request edge, so we'll take this picture for example, ignore the dotted lines and all the things I've written for right now. I'll come to that in a minute. A request edge goes from a process to a resource, and it is a directed arrow edge, which goes from a process to a resource, meaning this process is requesting for this resource. And assignment edge or allocation edge goes from a resource to a process or thread, meaning this resource has been currently allocated to this thread, right? These are the two types of edges we generally have in an RAG. Now when we implement the deadlock avoidance algorithm, we introduce a new type of edge called the claim edge. So what we do is, a claim edge from a process T to a resource R indicates that this thread may request the resource R at some time in the future. So basically, if you look at this from T2 to R2, this is a claim edge. It means T2 has not requested for R2 right now, but sometime in future it might want this resource. So right now T2 has only requested for R1, but at some time in future it might want R2 also. So this is what we meant when we looked at this point over here. You need the maximum number of resources of each type that a thread may need, which means right now I've asked only for this much, but in future I may need these many more instances of this type. So we assumed that this information is given to us, and then only we started with this process, right? So that information, this is where it comes in handy. So what is a claim edge? It's an edge again from a process to a resource, denoted by a dashed or a dotted line. It indicates that this process currently has not requested for this resource, but in future it may ask for it. Now when the process requests the resource, you convert the claim edge to a request edge. Then if it is suitable, if it is feasible, you will allocate, you will replace it by an assignment edge. Once the work is done, when the process returns the resource, so we saw yesterday, right, that once a process has finished whatever it wants, it returns all its resources. Again, you convert it back to a claim edge, right? So that is what generally claim edge is about. How do we use this to avoid deadlocks? I'll come to that. But as of now, what I want you to know about claim edges, it is represented by a dashed line from a process to a resource. It means this process has not asked for this resource right now, but will ask for it sometime in future. When it actually makes the request, you convert the claim edge to a request edge, and once it has been assigned, the work has bbeen completed, once T2 returns R2, the assignment edge again becomes a claim edge, right? So this is the role claim edges play in an RAG. Now, how does this help us detect a deadlock? So what you do is, this is basically a request that's going to happen at some time in the future, right? So if converting this request edge to an assignment edge does not result in the formulation of a cycle, then you say this is a safe state. Let me repeat that. So this is a claim edge, meaning T2 saying at some time in future I will need R2, I don't need it right now. So let us say that time instance in future comes, T2 asks for R2, at some time it is going to ask, right? So it asks, so this claim edge will become a request edge. Now supposing I allocate R2 to T2, so that request edge, I make it an assignment edge. I make it an arrow from R2 to T2. So that is what I am doing here. See, if you see, the rest of the edges are the same. T2 requested for R2, so I assigned it. So if doing that does not result in a cycle in the graph, then I will say this is a safe state. There is no deadlock. If there is a cycle, if converting that request edge or claim edge to an assignment edge results in a cycle in the graph, then there is no, this is an unsafe state. So again, remember, unsafe state, not necessarily deadlock state. Okay, so we will take a look at the example again. So T2 is requesting for R2 sometime in future, claim edge. So let us say at some point it makes the request. So the claim edge first becomes a request edge. Then I choose, as in the processor or the OS or whatever, choose to accommodate that request. So I assign R2 to T2. So I make an assignment edge over here. Everything else remains the same. Now if you see, there is a cycle in this graph, right? Cycle starting from R2 and coming back to R2 or wherever, which means this is an unsafe state. So this system is in an unsafe state. This may lead to a deadlock. So if I allocate R2 to T2, I am putting my system in an unsafe state, meaning it may end up in a deadlock, right? So what deadlock avoidance is happening here, you know what a claim edge is now. So basically, when you have prior information about this process might ask for this resource in future, you will see if it asks and if I give it, am I going to be in a safe state or unsafe state? You will convert the request edge or the claim edge to an assignment edge and you will check for a cycle. So if there is no cycle, it means in future if this process asks me for this resource and if I give it this resource, there is not going to be any problem. I am going to still be in a safe state, so there won't be any deadlock. Which means I can go ahead and allocate, I will allow the process to do its job and I will continue with the rest of the processes. However, if converting this edge into an assignment edge is going to put me in a cycle, put a cycle in my graph, it means if I do this allocation, if in future T2 asks me for R2 and if I give it R2, I am putting my system in an unsafe state. Meaning there is a chance that a deadlock might happen, there is a chance that a deadlock might not happen, but I am putting it in a risky state. So if I don't want to take the risk, if I want to avoid deadlock, I will not allocate this R2 to T2 at all. So this is how this graph helps you to find out whether you are in a safe state or not, and accordingly you can decide whether you want to do this allocation or you don't want to.